Did you know that the world's largest particle collider, the Large Hadron Collider or LHC, was restarted this year after a 3-year hiatus? The LHC is the world's most powerful particle accelerator, located underground between the borders of France and Switzerland. This massive donut-shaped collider smashes known particles together at extremely high energies using superconducting magnets and proton beams. Following a 3-year pause filled with improvements and maintenance, it promptly spotted 3 unusual particles for the first time. The LHC is now operational, setting records for the greatest energy particle collisions ever undertaken. The teams engaged are looking for further information on the so-called God particle, the Higgs boson, as well as evidence of dark matter. There's little doubt that the collider's recent enhancements are putting scientists on the verge of uncovering breakthroughs that might change our knowledge of physics forever. But has the LHC, which its detractors frequently refer to as demonic technology, yielded any darker, weirder, or unwanted discoveries? To discover more about it, keep watching to the very end. Hey there and welcome back to the Tech Edge. In today's video we are going to discuss this unseen discovery made by the Large Hadron Collider. But before we begin, make sure you subscribe to the channel and hit the bell icon to never miss any future videos. What is the origin of the cosmos, and why does matter instead of antimatter exist there? A decade ago, many physicists made international headlines when they found the Higgs boson, a long sought-after particle that gives the rest of the cosmos its mass, but is still missing nearly everything. Optimist scientists asserted that the universe was up for grabs, and that the Higgs boson was the Sun Collider's planned target when it was initially turned on in 2010. The Standard Model, a system of equations that describes everything researchers have been able to observe about the subatomic world, is built on the basis of this particle. However, the Standard Model is unable to explain some of the universe's most fundamental characteristics, including its beginning, the components of the cosmos, and even the reason why the Higgs particle itself has mass. Scientists are confident that recent discoveries may help to shed light on some of the mysteries surrounding dark matter and other topics, because they are able to find dark matter's gravitational signals. The bulk of the cosmos is made up of this dark matter, although its composition is yet unknown. The fact that dark matter is in charge of the universe's expansion is the most significant thing that scientists now know about it. It is difficult, if not impossible, to measure since it is so mysterious. Less than 5% of measured matter, including human tissue, is known matter, according to NASA. According to astronomers, the cosmos is filled tightly with dark matter, a material whose strong gravitational attraction prevents galaxies from merging, but which cannot be clearly viewed. The most current studies show that dark matter is 5 times heavier than visible stuff. Despite this, astronomers from all around the world have conducted dozens of thorough searches without success. Dark matter is buried in the mirror world, making it challenging to find. The realization that the majority of matter in the cosmos is actually invisible to us is astounding. One of science's open-ended questions is this one. In 2010, when the massive collider was turned on for the first time, scientists anticipated finding some answers. However, aside from the Higgs, no other new particles, particularly those that would have cast light on the puzzle of dark matter, were found. Because the invisible cosmic structure known as dark matter is what keeps galaxies and galaxy clusters together, astronomers conclude that it must exist. Although we are unsure of its specific nature, dark matter is undoubtedly one of the most fascinating scientific conundrums. Unfortunately, when the collider was shut down at the end of 2018 for extensive maintenance and improvements, the Standard Model remained unaffected. The collider will shut down for a further 2 years after 2025 in order to implement other significant upgrades. The huge detectors that sit at each of the 4 spots where the proton beams clash and examine the collision debris underwent alterations as part of this phase of upgrades as well. Since July, these detectors have been put to the test. Since there are many sprays of particles that need to be separated from one another, squeezing the proton beams confuses computers and detectors while also increasing the likelihood of protons colliding at the places of junction. Since then, other research has shown flaws in the prevalent paradigm and demanded a more in-depth exploration of the universe. The unique behavior of subatomic particles, whose names are mostly unknown to us in the cosmos, is the subject of these findings. Consider the muon as an elementary particle that temporarily gained notoriety in 2017. Muons are commonly referred to as fat electrons, since they are 207 times as heavy as electrons yet have the same negative electrical charge. Cosmic ray collisions and collider events produce muons, which in a matter of microseconds radioactively decay into a flash of electrons and spectral neutrinos. How muons fit into the overall picture is a subject of some debate. According to 200 scientists from the Fermi National Accelerator Laboratory in Illinois, muons rotating in a magnetic field wobbled noticeably faster than the conventional model anticipated. This discovery was made public last year. The quantum whisper of yet unidentified particles that would temporarily develop around the muon and change its characteristics was revealed by the value of a parameter called 2, which indicated a particle's response to a magnetic field to the 8th decimal place. There is a discrepancy between experimental findings and what is predicted by theory. It was thought by scientists to be the cause of the modest but significant departure, as the conventional model would eventually be broken in order to investigate nature at the tiniest sizes. The Higgs boson is both a potent telescope and a superb microscope since it has access to extraordinarily high energy scales. Physics, since it aims to degrade to a more accurate vacuum with less energy. Physicists refer to a vacuum as a false vacuum. The dips and hills in the energy potential of the Higgs field maintain our universe in this fake vacuum long enough for planets, stars, and galaxies to develop. This hypothetical vacuum will eventually deteriorate since it is fundamentally unstable. The artificial vacuum could be able to cross those hills and roll down the slope on the other side with the aid of quantum energy fluctuations or the weird quantum tunneling phenomena. We ought to be grateful for the current universe since only the Higgs field is preventing vacuum decay. Everything would vanish and be replaced by a genuine vacuum, which would radiate outward in a wave moving at the speed of light if the fake vacuum destroyed. Here is yet another attempt to understand the world, and these models are vital to the Hadron Collider's search for physics beyond the Standard Model. The Standard Model of particle physics, despite its numerous achievements, is by no means the last word on the matter. For instance, it does not suit cosmological theories that describe the creation of the universe. However, two groups of theorists are still attempting to match up their predictions of what 2 should be in order to wait for additional evidence from the Fermilab experiment. The muon, one of the 6 varieties of quarks that form up heavier particles like protons and neutrons, is another peculiarity. Currently, theorists are striving to match up their expectations of what 2 should be. The quark, the protagonist or antagonist of this story, is a component of the 2-quark meson particle. The instability and propensity to disintegrate of these quarks, however, seem to contradict the mainstream paradigm. The daisy chain of events that results in a new lighter quark and 2 light particles known as leptons, which may be electrons or their fat relatives muons or both, is one uncommon way that a quark might decay. Both electrons and muons are expected to appear during this procedure. Despite the Ta being a third heavier lepton but decaying too rapidly to be observed, Dr. Patel and his colleagues have found more electron couples than muon pairs, which goes against the lepton universality principle. Dr. Patel thinks a leptoquark, a subatomic particle, would be one of the most dramatic possibilities if these results hold up in the upcoming collider run. This anomaly suggests an unknown influencer, a particle of force interfering with the process, similar to how the muon's magnetic anomaly does. If the particle is genuine, it may close the gap between the quark-based protons and neutrons that make up the material universe and the heavier leptons, such as electrons, muons, and neutrinos. There are temptingly 6 distinct lepton types and 6 different quark types. According to Dr. Patel, we are starting this marathon with more hope that a revolution may be on the horizon. Another particle in this unusual assortment is the W boson, which carries the so-called weak force responsible for radioactive decay. The 10-year endeavor to determine the mass of this particle was announced in May by the collision detector at Fermilab, or CDF. About 4 million bosons from collisions in Fermilab's TeV were used in the effort. Before the construction of the Large Hadron Collider, the W boson should weigh roughly 80 billion electron volts, making it the most powerful collision ever. The Higgs boson, in comparison, has a mass of 125 billion electron volts. According to the experimenter's 7 sigma estimate, where the likelihood of a mistake was just 1 in 2 trillion, the WETF measurement, the most accurate measurement ever, came in at 80.433 billion, which was higher than anticipated. This difference was a statistical outlier. The 3 anomalies all point to undiscovered forces or particles that conflict with accepted physics. However, with further information, they may all vanish along with the revolutionaries' dreams. Optimists had reason to be hopeful when Kyle Kramer, a University of Wisconsin physicist involved in other CERN research, said that a new particle that would explain both 2 and the mass would be found at the LHC. Researchers will utilize the LHC to study the more delicate interactions of the Higgs particles and look for signs of the mysterious dark matter, which accounts for around 27% of the universe's substance but has never been directly detected. As a result, even while the LHC won't rip time and space apart, it could nevertheless enable researchers to shed light on some of the universe's secrets. We will make sure to keep you informed as soon as they solve any new riddles. Do you believe that this finding will alter how the cosmos functions? And what makes you believe that? Let us know in the comment section below. Thanks for watching. Stay safe.